For Lesson 6, Chapter 6, we'll be looking at electromagnetic radiation. We're first going to talk about light and its dual nature as both a wave and a particle, and we'll learn some equations where we calculate wavelength, frequency, or energy of a wave, and also define the Heisenberg uncertainty principle. Here's a list of some new vocabulary words that we'll discover in this lesson, as well as 3 equations that we will be using throughout the chapter. Light can behave both as a wave, but also as a particle. So we're going to first look at light as a wave. When we're exploring light as a wave, we're going to be using the equation below, C is equal to lambda V. We're going to look at and define what those variables mean and how we're going to use them. So first off, looking at wavelength, represented by this lambda symbol in blue. So what is wavelength? It is defined as the length between 2 crests or troughs. So we measure this length in meters. Now, when we're talking about crests, those are the 2 highest point of a wave. So looking at the figure off to the right, it would be the very top of one wave to the very top of the next wave. That will be one wavelength. When we're talking about troughs, that would be the lowest 2 points. So in this diagram off to the right, there's only one trough in the picture. If you can imagine, the other one would be a little bit further down, exuding the same wavelength as if you measured by the crests instead. Once again, this does need to be in meters when we're using it in the equation. A lot of times it is given to us in nanometers, so we will have to convert from nanometers to meters before putting it in the equation. So just be aware of that. And 1 nanometer is equal to 1 times 10 to the negative 9th meters. And we'll see that very frequently when we do these problems. Next variable is frequency, represented by this letter V. So frequency is defined as the number of complete waves passing a point over time. So since it's the number of waves over time, the units on it are inverse seconds, often written as seconds to the negative 1 power, indicating that it's inverse seconds. Another way to represent this would be as a fraction with 1 on top and then the second units in the denominator. It's important to note as well that inverse seconds is the same as hertz. So all 3 of these units are interchangeable and mean the same thing. So to calculate frequency, how they do it is they pick a point and count how many waves cross that point over a certain amount of time. Now the last variable in the equation, variable C, represents the speed of light. So the speed of light is a constant that was calculated many years ago, and the value is 2.998 times 10 to the positive 8 meters per second. So this is a memorized value that you'll be using in this equation. And notice the units on it is why we need the wavelength measured in meters and why the frequency is measured in inverse seconds. The electromagnetic spectrum shows the different types of electromagnetic radiation, and it's arranged by wavelength. More specifically, it's arranged by increasing wavelength. So if you can see on the bottom of this diagram, we have the lambda symbol and then the values increasing as we move to the right. You'll also notice that it's arranged by decreasing frequency. So you can see the frequency values at the top here, and they are decreasing as we go to the right. So it would stand to reason that frequency and wavelength are inversely proportional. What that means is when one goes up, the other goes down. So they always go in opposite directions. So if the wavelength is increasing, the frequency is going to decrease. If the wavelength is decreasing, then the frequency is going to increase. And this is due to the fact that the speed of light remains constant, has a constant value. I also want to point out the small section, the visible section, of the spectrum right in the middle. So you can see this visible portion, very, very tiny in the middle. I'm circling it here in red. So this is the part where we can see colors, differentiate colors with our eyes. So when they highlight this and expand the visible spectrum, you'll see it ranges from 350 up to 800. Now notice the units on this visible spectrum that is highlighted here. It's nanometers, not meters. Okay, so it is in nanometers. So it's going from purple at the low end of the wavelength all the way up to red at the higher end of the wavelength. So we'll be exploring the visible spectrum quite a bit, especially in lab. So let's take this new equation that we've learned about with all the variables and try to solve a problem using it. So in this practice problem, it is asking us for the frequency. So if you remember, frequency is represented by that variable v. So frequency of a wave, and they're giving us the wavelength. So wavelength is represented by the lambda symbol in the equation. Now notice the units on wavelength, they did give it to us in meters, which is nice. That means we do not have to convert. So we know the wavelength, but we also know another piece of information not specifically given to us in the problem. We know what the speed of light is. It's 2.998 times 10 to the positive 8 meters per second. So we actually have two knowns, the unknown then being frequency. So we use our equation, which is c is equal to lambda v. We'll rearrange the equation to solve for frequency. So in order to do that, we divide both sides by the lambda, getting frequency by itself. So the equation becomes frequency is equal to the speed of light over the wavelength. Plugging in those values, speed of light in the numerator and then the wavelength in the denominator, we get a total value of 1.14 times 10 to the positive 17 hertz. Now keep in mind that hertz is obviously an acceptable unit. You might also see that 1 over s for inverse seconds, or s to the minus 1. They are all acceptable units because they all are equal to each other. Right, here's another practice problem. Feel free to pause and try on your own. So it is calculating the frequency once again, and the wavelength is given. Now notice the wavelength is in nanometers this time. Now I put the conversion factor in parentheses after. They are not going to give you this conversion factor on an exam because it is a metric to metric conversion. So the metric to metric conversions are the ones you have to memorize. Okay, so 1 nanometer is equal to 1 times 10 to the negative 9th meters. So we're going to use that to convert the nanometers to meters first, and then we'll solve for frequency. So the first step is taking that 975 nanometers, multiplying it by 1 times 10 to the negative 9th, so that putting the nanometers in the denominator so they cancel, and that gives us 9.75 times 10 to the negative 7th. Looks like I forgot to put units on there. That's going to be meters. Now that we have that value in meters, we can solve for frequency. So once again, the equation's rearranged with the speed of light on top in the numerator and the wavelength in the denominator. When we divide those two, the meters cancel, leaving us with inverse seconds or hertz for our answer. Also notice we have 3 significant figures in our answer because that's how many significant figures were in the value given to us in the problem. Let's look at one more problem, and this time we're going to apply it to the electromagnetic spectrum. So for this time, we're using the same equation, but we are solving for wavelength instead of frequency. What is the wavelength? Now they gave us the frequency. Notice the units on the frequency. They gave it in megahertz. Now we want it in hertz, not megahertz, hence the conversion factor given in parentheses at the very end of the problem. Now the second part of the question is asking what is the type of radiation, And what they're asking by that is, once you solve for the wavelength, the type of radiation means where does the wavelength fall on the electromagnetic spectrum. So you do not have to memorize the electromagnetic spectrum. If they ask a question like this on the exam, they will give you this electromagnetic spectrum and you just need to refer to it and figure out which area it lies in based on your wavelength value. You could also probably already figure it out just by knowing what the frequency is as well, since frequency are the top numbers here on the spectrum. So looking at what we know, we have the speed of light, the value c. We also have the frequency in megahertz. So our first step is going to be, to convert the frequency from megahertz into hertz and then plug it into the equation. So converting to megahertz, shown here, we multiply by 1 times 10 to the 6 hertz, putting the megahertz in the denominator so they cancel. Once we have that value, we can then plug it into our C is equal to lambda V equation. When we plug it in to that equation, we have the speed of light on top and the frequency in the denominator. Dividing those two numbers, we get an answer of 3.82 times 10 to the negative 7th meters. So now that we see what the wavelength is, to answer the second part of the question, we find this wavelength on the electromagnetic spectrum, and it's time 10 to the negative 7th. So that would be right around in this region, where 10 to the negative 7th is in the wavelength section. And that is looking like visible light, violet light. So you can see it's encroaching, so 10 to the negative 7th is between here and here, these two dashes. So it was either going to be near ultraviolet light or visible light. So far, we have explored how light can act as a wave, and now we're going to look at energy in light and also how light can act as a particle as well. So we do this by looking at the photoelectric effect. So the photoelectric effect is essentially when you shine light on a metal surface. If that light has really short wavelengths, so short wavelengths meaning very high energy, that light can actually eject electrons off of that metal surface. When it ejects those electrons off of the metal surface, this is called the photoelectric effect. And it's showing that light can also act as a particle, hitting those electrons off. When we describe light as a particle, we refer to those particles as photons. So photons is defined as a particle representing a single packet of light energy. So in this photograph, off to the right, we have a flashlight shining, and there are two representations of the light that's shining out of that flashlight. We have the wavelength representation along the bottom, where you can see the wavelength would be between the two troughs in this case, so from the lowest point to the next lowest point. So this is how light would act as a wave. But then in the top portion, we have the flashlight showing how light acts as a particle. So you see these little photon particles just kind of flying around, ready to hit a metal surface and knock some electrons off of it. So when light acts as a particle, we have a different type of equation. Since there is no wavelength involved when it's acting as a particle. So that equation is going to be represented here. So E of a photon stands for energy of a photon. The units are joules per photon. And then we have two other variables in this equation, H and V. Now we already know what V represents. That's frequency. So that's going to be the same as the previous equation we learned, C is equal to lambda V. But H is a new variable. Now H is a constant, just like c, the speed of light, was a constant, so it will always have the same value. And that value is 6.626 times 10 to the negative 34th joules times second. We refer to this constant as Planck's constant, and we use it in this energy photon equation. Now, the frequency part of the equation still is going to have the same units as before, measured in inverse seconds or hertz. If they give you a value in megahertz, make sure you convert it to hertz before putting it in the equation. An important thing to note with this equation as well is that the energy of a photon is directly related to frequency. So that means proportional. So the higher the frequency, the higher the energy. So frequency goes up, energy goes up. Frequency goes down, energy goes down. So they follow the same line, proportional to each other. Let's try a practice problem with the new equation. So we're going to calculate frequency, and they want the answer in megahertz. So whenever we use one of these equations, we've learned if we calculate frequency, the units on it are going to come out in hertz. So our final step will be to convert it into megahertz, since that's what our final answer needs to be in. So the frequency of an emitted photon, and they're giving us the energy of that photon. The energy being 6.89 times 10 to the negative 23 joules. Notice the conversion factor is given going from megahertz to hertz. Now, this is a metric to metric conversion as well, because mega is a metric unit. So this conversion factor will not be given to you on the exam, just like the nanometer to meter conversion factor would not be given to you. So you'll want to remember these two, since there's not a shortcut way to do those metric to metric conversions. All right, so what do we know? We know the energy of a photon they gave to us. We know Planck's constant, because that's always the same, and then also the conversion factor. So we need to determine the frequency and convert it to megahertz. So first step would be to rearrange the equation to solve for frequency. So to do that, you need to divide both sides by Planck's constant to get frequency by itself. So then you will have energy of the photon in the numerator divided by Planck's constant in the denominator. Dividing those two values, you can see that the units of joules cancels out, leaving us with units of inverse seconds, which is the same as hertz. Now this is not the final answer, so we don't have the correct sig figs yet, because we need to convert it into megahertz next. So converting it into megahertz, we get a value of 1.04 times 10 to the positive fifth megahertz. So this next problem, we're calculating the energy of a photon. So since we're calculating energy of a photon, we only have one equation so far that we've learned that represents energy of a photon, and that is Planck's constant times the frequency. But notice they're talking about how this energy of the photon was absorbed in the blue-green region of the visible spectrum, and they give us a wavelength. That's what that 486 nanometers is. That's a wavelength. So we can't use our original equation for energy, because all that has in it is Planck's constant and frequency. And although we know what Planck's constant is, we don't know what the frequency is, and we don't know what the energy of the photon is. So we have two unknowns in that equation. So this is going to be a two-equation or two-step problem. If you're counting converting from nanometers to meters, it's actually going to be a three-step problem. So here's the layout of how we're going to go through the steps. So first step, of course, is to convert, make sure everything's in the right units before you plug them into equations. So start by converting the 486 nanometers into meters. We do that by multiplying it by 1 times 10 to the negative 9th meters. Nanometers cancel out, and we get 4.86 times 10 to the negative 7th meters. Now from here, The only equation that we have that has wavelength in it is the C is equal to lambda V. So that was our first equation we learned in this chapter. So if we rearrange that equation, as you can see here in step 2, to solve for frequency, we can take the speed of light, 2.998 times 10 to the positive 8th meters per second, divide it by our wavelength given to us in the problem, which we have converted to meters. When we divide those by each other, we get a frequency of 6.17 times 10 to the positive 14 hertz. So now we have a frequency, which is nice because now that we have a frequency, we can go to our original energy equation and plug in Planck's constant and frequency. And that's exactly what we do in the last step. Planck's constant, 6.626 times 10 to the negative 34th joules times second, multiplied by our frequency, which is in hertz or inverse seconds, meaning this inverse seconds cancel, and we get energy of a photon of 4.09 times 10 to the negative 19th joules for the units. So in the previous problem, we were solving for the energy of just a single photon. Now remember, a single photon was just a small packet of light energy. It's how energy behaves as a particle. So very small particle. Now what we're going to look at, instead of the energy of just one individual photon, is we're going to look at molar light energy. So molar light energy is how much energy in a mole of something. Okay, so since we're talking about moles, you can guess that we're going to use Avogadro's number, because if you remember way back from, I don't know, it was chapter 2 or 3, Avogadro's number is what defined what a mole was. Okay, so for Avogadro's number, so far we've used it representing atoms or elements or molecules, but now we can use it representing photons. So using Avogadro's number to represent photons, it can become a conversion factor of sorts, where 6.022 times 10 to the 23rd photons equal 1 mole. So this is going to help us convert our units of joules per photon, which is what we just did with the previous equation, into joules per mole. So that's how we're going to use that, converting it from joules per photon to joules per mole. Why is this important? Why are we even doing this? Because photons don't just interact with one atom. Okay, it's light. It's speed of light, very fast, right? We saw that. It was 2.998 times 10 to the positive 8th. So moves around at its own will, and it's going to hit what it's going to hit. It's not going to purposely just interact with one single atom. So if a mole of atoms are present, then that 1 mole of photons is going to interact with each atom because they're moving so quickly. So this is why we need to be able to calculate molar light energy and not just per photon. Calculating molar light energy takes 3 distinct steps. So we're going to go through each of these steps and how to use them and do some example problems. So starting with the first step. First step we've already done. It's using the energy of photon equation, taking Planck's constant multiplied by frequency. The second step is to use Avogadro's number to convert that energy of a single photon in the first step to energy of a whole entire mole of photons. So this is essentially how it's going to look. You're going to take the energy of the photon that you calculated in step 1. Now the energy of the photon, the units on it, are joules per 1 photon. So you multiply that then by Avogadro's number. Why are you multiplying by Avogadro's number? Because Avogadro's number, units on it, are photons per 1 mole. So by multiplying by Avogadro's number, you can see that the photons are going to cancel out because you have photons in the numerator in Avogadro's number and then photons in the denominator from that energy calculation in step 1. So with photons canceling, you can see the only units left are joules per mole. And that's exactly what we're trying to calculate here, is the energy in joules per 1 mole of photons. Now the last step is calculating the total energy. So how do we calculate the total energy? We're going to take the number of moles multiplied by the energy of 1 mole of photons. Okay, so what are these things? Where do you get them? Well, the number of moles is going to be given to you in the question. So this number of moles here, that'll be part of the question. They'll say, what is the total energy in 1.5 moles? Okay, so they'll give you that value in the question itself. The part you need to figure out is the second part, and that's what we did with steps 1 and 2, is calculating the energy of 1 mole of photons by first calculating the energy of a single photon and then multiplying that by Avogadro's number to get it in moles of photons. The important thing to note is always check units. Okay, so sometimes they give you different units like kilojoules instead of joules, so you might have to convert. So just always double check your units, especially throughout lesson 6, because there's lots of nanometers, there's lots of megahertz, there's lots of kilojoules. So just be vigilant. All right, so let's try a problem using those 3 steps. So what is the total energy? So the fact that they're asking total energy means that we're going to do that 3-step calculation. Notice they gave us the amount of moles used in the very last step, 3.65 moles of photons, and then they gave us a frequency in megahertz. So this is why you want to pay attention to units. So we're going to first want to convert our megahertz units into hertz, and then we can calculate the energy of a single photon by multiplying Planck's constant by the frequency. So here is what we know. We have the frequency, which will convert into hertz. We have Planck's constant. Avogadro's number, that's going to be our second step. So once we have the energy of a single photon, we'll use Avogadro's number to figure out the energy of a whole mole of photons. And then once we have the energy of a whole mole of photons, we'll multiply that by 3.65 to get the total energy. So converting first, frequency into hertz, we are multiplying by 1 times 10 to the positive 6 to get a value of 4.83 times 10 to the 17th hertz. Now that we have it in the correct units, we go ahead and calculate the energy of a single photon by taking the frequency that we converted multiplied by Planck's constant, and we get the energy of a photon to be 3.20 times 10 to the negative 16th joules per photon. So that's energy of a single photon, so we want to multiply that then by Avogadro's number to get energy of an entire mole of photons. So that's what we're doing here. This is Avogadro's number that we're multiplying it by. Photons and photons are canceling, and now we have energy per mole, joules per mole. So our last step to go to total energy is to take this energy in joules per mole and multiply it. Excuse me, let me erase this so you can see that last step a little bit better. Multiply it by the moles they gave in the problem. So the 3.65 moles they gave in the problem, multiplied by the energy per mole we calculated to get a value of 7.03 times 10 to the positive 8th joules.